one that Barry Mariba
Yeah. How have you not looked up what the Barry-Mariba function does? So it's very interesting. I mean, you should have looked it up beforehand. The barrier function that Barry Mariba did during his PhD thesis is about robust linear regression. It's like the Huber loss. Okay. So if you check on the papers, it's an alternative to the Huber loss. Right. So Barry Mariba's, I found out about this function because if you read any biography of Barry Mariba, it always mentions the fact that he invented the barrier function during his PhD. So I looked up what the barrier function is, and it's for robust linear regression. It relates exactly to what we've been doing. It relates to the case where you've got non-Gaussian data. Remember we've talked about that? But he actually is looking at the frequentist perspective, the loss perspective, which is different. So in that case, you don't write down a probability distribution for what you think is going on. You write down a loss. And there's something called the Huber loss, or the Huber function, which people use. It's like, I think it's just the exponential distribution. It's the absolute value or something related to that. I've not really used it. Barrier did an alternative loss. And so it's the barrier loss. We should have had him along. Well, we should have done an honorary session where we talk about the barrier loss and how it's covered. Yeah. So I only read that because we had holiday yesterday, so I didn't know that before. So that was a little sidetrack. This is the book that has all the information you need to do about Gaussian processes. The things we've covered so far are mostly covered quite rapidly in the first chapter. And what we're now going to do is, so far we've been interested in Bayesian inference, and we've been interested in linear regression and parametric models. We're now going to take a completely different perspective on how you fit a model. So, what I just said was, in fact, what we ended up doing in the Bayesian part was we ended up writing down a marginal likelihood, where the marginal likelihood had this form. Probability of y is equal to a zero mean Gaussian, and y is the vector of all our observations, with a covariance of that form. Yeah? That's what we just said was the marginal for multivariate Bayesian regression. Yeah? That is a probability distribution directly on y. So in Gaussian processes, it turns out that if you look at models from this perspective, you worry about the marginal likelihood. You can do more powerful things than you can do with standard linear and basis function based regression. So this becomes our starting point. So it's a different perspective. Why? I mean, not why. Now when I'm saying why, I mean this why. Why? Not that why. Why is it a different perspective? Because we're putting a probability distribution over y, and look at it. It specifies correlations between our data points. This object here is a covariance. When we were looking at linear regression before, we put that type of model on it. Not on y, but on the noise. That the probability distribution of epsilon is just that. That's the noise model. And remember I said what we're going to do now is add stochasticity to the world model. The noise model is the world model, to our model, our belief about what's going on. Adding that stochasticity to our model gives us this term, which is a load of correlations between data points. That's independence between data points, that's IID. These are correlations. This is the bit we're interested in. And specifying the correlations directly is what Gaussian process models are about. So we're going to consider, for this next part, a Gaussian PDF with a particular structure of covariance. And what I'm going to show you in a moment is one sample from this Gaussian PDF with a particular structure of covariance. So we're going to sample a point, a single point, from a multivariate Gaussian, which is 25-dimensional. So it's a 25-dimensional Gaussian with correlations. We're going to sample one point, and I'm going to plot that point against its indices. So this is the form of the covariance I used as a color map. So what this covariance is saying is index 1 and 2 are very close to each other because there is a covariance, but it's also a correlation because the diagonal I've set to 1. So the correlation between points 1 and 2 is about 99%. So any neighboring point is 99% correlated with each other. But then as we move away, as we get 5 points away, we're close to like 55% correlation. Yeah? So 1, 2, 3, 4, 5, we're in yellow. The correlation is down at 55%. Yeah? So that's the form of the covariance. And this is the form of one sample from that covariance. One sample. What does it look like? Looks like a nice function. Now this is odd. I think this is odd. I think the first time you do this, you find this is odd. Because people expect, when they sample from Gaussian distributions, to see something noisy. To see something which isn't, when I say noisy, that's the wrong use of the word. To see something that's non-differentiable. If you just sample from Gaussian white noise, you'll see something. If you connect up the samples, we haven't connected up the samples because it's not quite clear why we'd have a reason to do so. But mentally, you can't help because you're human. You're connecting up these samples in your head and you're seeing a function. Yeah. Now it'll turn out that not only is this function differentiable, it's infinitely differentiable. It's infinitely smooth, which is completely against people's intuitions about what you get from a Gaussian. And the reason is because people don't normally consider these types of correlation structure. It's arising from this particular type of correlation structure, giving you the covariance, giving you this smooth functional form. So, since this is a probability distribution over functions, and that's a function, we can consider this potentially as a prior distribution for functions. Now, what I want to do to investigate what's going on here in a little bit more detail and to show you what inference in Gaussian processes is like is look at these 2 points on the end here, yeah? So I've just circled them, I'm making them flash. There, points 1 and 2. Now, Gaussians have a remarkable property, which is if we want to know the covariance of those 2 points, we have to integrate out all these other points, yeah? So this is a distribution, is a probability distribution over F1, F2 to F25 that we've sampled from. Those 2 points there, we want a probability distribution of F1 and F2. So in order to get that, I have to use the sum rule and integrate from dF3 to F25, yeah? Now integration is difficult, particularly high dimensional integration, apart from in Gaussian distributions, because high dimensional integration involves doing this. I put a box around those first 2 elements of the covariance. The result of that integration is a Gaussian with this covariance. It's the marginalization property of Gaussians, that the covariance stays the same. This is quite important any type of correlation analysis, because bear in mind the covariance of the Gaussian underpins correlation analysis. If correlation were to vary depending on variables we hadn't measured, yeah, then correlation would be meaningless. So it's what leads to correlation analysis as well. But in this case, it's allowing us to integrate out all the points apart from those 2. And then I've just replaced here with the actual values in that matrix. So this is the covariance matrix for those 2 points. 0 mean, this is the covariance. Very high correlation, 0.96 correlation. Now let's plot what that marginal distribution looks like. So this is the marginal distribution between F1 and F2, yeah? So if we did this with weights and heights, right? You could sample from if you sample from F1 and you know you're up here, then you know, sorry, if you sample from F1 and you know you're up here, and you know F2 is also likely to be up there. So what does that mean in practice? Well, let's say someone tells us what a value for F1 is. So this is an observation for F1. Sorry, F1's just off the board here on the left. This is F1 in this axis. So we're observing F1 is along here. Well, the way we then say, if we know F1, given F1, what's the distribution for F2, is that physically it's that slice through this Gaussian and then the projection on to look at what that slice through this hill looks like. So if I just renormalize that and plot it, it looks like that. So the conditional distribution of F2, given F1 is here, is in this region here. So F1 is slightly negative, and because F2 is strongly correlated with F1, its mean, its most likely position is right here, which is also negative for F2. But it's got a variance associated with the width of this sort of distribution here. Yeah? So that means we can sort of, given this covariance structure and one observation for F1, we've got a distribution for where we think F2 should be. Or we could ask the question, what about F5? So, oh, and by the way, if we just look at the samples, we happen to take F1 and F2 are both in the negative quadrant. It's not impossible that F2 could be positive because look, there's this probability here that it's positive, yeah? But it happens to be negative. It's most likely to be negative. So, yeah, so that's the sample actually. That's where F2 was in the plot before. I've just marked it there. It happened to be there. Now, that requires a little bit of Gaussian manipulation. So this predictive distribution here is key. Even though the original distribution was zero mean, our prior was zero mean, the posterior, once we've observed what F1 is not zero mean. That's the mean here. You can sort of work this out mathematically. What I'm showing you mathematically is what generated this Gaussian here, yeah? So even though, because of the correlation, if there's correlation between 1 and 2, if this is 0, the mean is 0, yeah? So if they're independent, it's still 0. But if there's correlation, then you end up with a mean that is the correlation between the two of them divided by the variance of 1 on its own times the observation of F1. So if the correlation was 100%, then you would just say that F1 would be F2, yeah? Because this would be K11 divided by K11 if the correlation was 100%. If the correlation was 100%, this term would also be 0. It would basically say, F1 is equal to F2. But what happens on this side here, this is the marginal variance for F2 before you make any observations, right? That would be the marginal variance for F2. 0 mean, variance K22. So when we've observed F1, we suddenly get a mean, and we also get a reduction in the marginal variance. This term here is subtracted from K22. So you go from, if we think about what the F2 marginal variance was before, it actually goes from there to there. That's its standard deviation. I've drawn these lines at one contour of standard deviation. The marginal variance is looking at this hill from the side. Both marginal variances are 1. But giving the observation of F1, the marginal variance has collapsed. Yeah, so we've lost some marginal variance, and you always do that if you've got correlation. If there's no correlation, this term here is 0, and you just still have the marginal variance. So if there's no correlation, nothing happens, obviously, because the things are independent. But if there's any correlation, you gain a little bit of information about F2 given F1. So yeah, that's where the covariance of the joint density which we've seen before. So because in this last example, K12 was 0.96, we move things quite a lot. 0.96 divided by 1 times F1 is the mean. And this is 0.96 squared divided by 1. So it's 1 minus 0.96 squared is the variance. So actually the standard deviation, I don't know, no, I can't compute the standard deviation in my head.
Sorry,
yeah.
This is what the notation. The mean. What's the
so the mean is K12 over K11 times F1.
What's the notation of the F2 bar?
Ah, sorry. Yes. So I defined, I should have been clearer. When we started on this little journey. I've defined the sample to be f. Okay, why have I done that? Because we've used this notation before to sort of say, so what's actually secretly going on here is I'm warming up to y being equal to f of x plus epsilon, and I'm sampling from our model of the world. So I tend to view y, so f is our model, whether that's mx plus c, or w transpose x, or now it's a Gaussian process. So that's why I use f to represent this. And then y is the corruption of what we've said about the world by the world model, the sort of the stochastic noise. So I'm using f to represent observations from the function. So f is the thing we're observing here instead of y. It could be y, and it wouldn't be that confusing. It'd probably be less confusing if I'd said y. So you can think of it as y if you like, but it's just a variable. So the joint distribution here is over f1, f2. And this is the conditional distribution of one f given the other, and this Gaussian, yeah? So we can repeat that process for f5. So f1 and f2, going back here, so this is f1, this is f2. I've just lined up the points along their index, and f5 is 3, 4, 5 is the point that appears here. So marginally before we start, it's got a distribution like this. This is one sample from the joint distribution where the value for f5 is close to 1. So doing the same thing, looking at the correlation between f1 and f5, the correlation is a lot smaller. Yeah, it's now 0.57. Now, I like to say that this is still a correlation that a lot of statisticians get very excited about, this type of correlation. I mean, it's still, 0.57. If you look at data, just so you're looking at data as a statistician, and you get a correlation of 0.57, you think there's something going on there. But just to show you, this is actually a very weak correlation, look, compared to what we just looked at, 0.96. And you get much less information about f5 given f1. There's the conditional distribution. Look how massive it is. Remember, the margin of the initial distribution is centered at 0 and has a standard deviation of 1. This thing's not far moved. It's just shifted slightly to the left, and it still has, the standard deviation will be probably around here. I'm not sure what it is. So we get in this case, we've observed f1's negative, but f5 is only slightly more likely to be negative than before. And indeed, if we look back at the sample of f5 we got when we did the joint sampling, f5 isn't negative at all. It's positive. Sorry, it wasn't close to 1. It's around 0.4. And that's not that unlikely. If you look at the conditional distribution, 0.4 would be about here. It's well within one standard deviation of the mean of the conditional. So this loose correlation means that you don't get such a good match between the two. And as you move further away, that happens further and further. So the things that are very close to f1, close in index, turn out to be close, and the things that are further away turn out to be further away. But of course, for each of those, what I've just said is true for each individual pairing of these points. These two are always strongly correlated. These two are always strongly correlated. So you've got this structure in the covariance which is giving us this functional form. This one doesn't have to be so close to this one, and is completely independent of this one. Yeah? But they need to be close to their neighbors. That's the structure of the covariance we used. Now, we've sort of done this, what we're doing here is training and testing for one observation. So the funny thing we've got going on here is we have a prior that apparently can generate some sort of nonlinear function, yet we can take one point and make a prediction for what the other point is, for any point along the line, even though we're considering nonlinear systems. Very nonlinear systems. And that's because of the sort of magic of Bayesian inference. But we want to predict. We probably often have more than one point, right? People might give us 25 points. And we might need to test over 300 points. So the general equations are this. These are just the conditional distribution equations for a multivariate Gaussian. that if our training data is f, a vector f, and our test data is a vector f star, we can make predictions about f star given f using this formula here. So in this formula, that's the mean. That's the inverse of the covariance of our training data. This is the cross covariance between our training data and our test data. So the formula we saw before was the special case of this, where f is one-dimensional. We actually had this underneath that, where these were both scalars. So this is the matrix form of that equation, multiplied by the vector of training observations. And here's the covariance. Again, that's the prior covariance of the test points. Yeah, this is the notation I'm using here. This is the prior covariance associated with the test points. This is the prior covariance associated with the training points. These are the cross covariances between training and test. And again, we get the same thing. You get the prior covariance minus the cross covariance times the inverse of the training times the cross covariance. Before we saw this as k12 squared divided by k11. Yeah. Here we're getting k12 inverse k11 k21. In effect is what this is saying, or the other way around. Once again, if there's no correlation between our training and test data, all we recover is that is 0 because this is 0, and this is 0 here, so we just recover the prior. Yeah? We recover the prior covariance. I'm always assuming 0 mean for our prior distribution on these Gaussian processes. You don't need to, it just makes the math simpler, and a lot of the time people assume that in practice. This is our prediction equation. This is the core of the Gaussian process. You can specify everything in the world with this equation. So we could make f star the current water temperature 300 meters under the ocean just off Hawaii, and we could make f the incidence of, or the rate of malaria infection in Kampala. Right? Those could be any two values in the world, as long as you have a correlation between those two values, a covariance between those two values, and marginal distributions about what those values were without knowing knowledge. You can use this equation to make a prediction between those two. Yeah? I mean, in that case, we'd hope the correlation is 0. I mean, it's going to be 0, I'm hoping. But believe me, this is a model of the world. Because of the marginalization properties in Gaussians, you can put anything in there and anything in there. But your world model, this is Ernest's question of the other day, where does the basis come from? Well, it turns out that the basis is what's specifying these matrices here, is what's specifying our correlation. If you believe in a Gaussian world, which we can't because of all the things we've talked about already, but it's actually still a really, really powerful model, what you need to be able to do is specify the correlation between the thing someone's given you and the thing you want to predict. Yeah? You want to specify that relationship in terms of correlation. You're no longer specifying a parametric model. Implicitly, that parametric model, if it's Gaussian, does specify a correlation. But this is a much more general framework. Yeah? Really, really powerful. And I think if you sort of get that message about it, then we've done well on the summer school. So it's a bit of a weird framework because we don't write down a simple model, y is equal to w transpose x, where we can see some simple equation plus independence in the noise. What we specify is correlations, or covariances, strictly speaking, but you can always recover the correlation, but you need to specify the covariance, between the thing you've been given and the thing you want to predict. And if you can get that, and we'll talk a bit after a break about how we get that in a moment. Okay, questions before we go to a break? It's sort of, I hope that's confusing, because it is confusing. If it's not confusing, I haven't explained it. I mean, it took me a long time to get to grips with this, because typically you get taught a lot about parametric models, and in parametric models you're constantly being told about IID, independence, identical distribution and independence. This is really a completely different perspective. It's saying, I need to specify the correlation. So how is it that we kept specifying the independence before and now we're specifying the correlation? Well, that's because in our modeling framework, where f of x is what we're specifying, we've made f of x stochastic. Once you make f of x stochastic, you're specifying something about correlation. The independence is for this guy, the model of the difference between the bit of the model that handles the difference between what you're saying and what the world's really like. But all the interest is here, all the work goes in here, and when you start being stochastic about this part here, you find you need to specify the correlation between the two test data points. That's what you're doing when you're modeling. And I think once you get your head around that, it makes a load of problems much easier to solve. So maybe, I don't know, maybe you're all thinking this is clearly a better way, but...
How would you relate, for example, if I had a scenario where I was looking at water quality in Lake Victoria and the death rate of fish, how would I compare it?
Oh, fantastic, lovely example. Water quality in Lake Victoria. Where in Lake Victoria, though? And the death of fish. So, but where are we specifying the water quality?
To know whether maybe the fish will...
Yeah, but what have we got in terms of measurements of water quality? Are we measuring it across the lake, or have we measured it at a single point, or have we measured it...
It depends. It depends.
It depends. Okay, so let's assume we have some measurements of water quality in Lake Victoria, right? So how would you come up with death of fish? Well, it's a nice example because and now I'm going to show how bad my geography of Uganda is. So there's Entebbe here, then Kampala here, right? And there's some other stuff up here. There's a big lake here. This is Lake Victoria. By the way, it can't be called Lake. It wasn't called Lake Victoria. People had noticed the lake before they called it Lake Victoria, I assume. What's it called? I can't pronounce. Narubai. Okay, in Luganda, but I presume I presume in Tanzania it was called something else.
Yeah, it was different.
So maybe Victoria's safe. Yeah. Okay, so we've got water measurements in Lake Victoria, and maybe we only can take them at some locations where we've got monitoring stations, and maybe the fishing is going on out here. So now you've got an issue about potential currents in Lake Victoria. I don't know with an inland lake how much currents you get, but if it was the sea, certainly you might have currents flowing along. And you would need to be able to say, well, what time was I measuring the water quality at? And then you would need to have a model of when the water was likely to arrive and kill the fish. And you would need to have a model of how many fish would die. I mean, the things you'd be measuring would be non-Gaussian. So one of the things that Ricardo, my PhD student, is working on with Martin is how you take an underlying Gaussian function. So if the corruption of the function is not Gaussian, if it's like the Gaussian thing is predicting a rate and then you're seeing fish deaths. So there's a rate of fish death, but rates are positive only, so they're also not Gaussian. So we might look at a log rate of fish death, the logarithm of the rate of fish death, and model that as the Gaussian process. And then we might want to correlate that with the log concentration of pollutants in this region here. And people build models of the pollutants. I mean, people do rather nasty things. They just put animals in tanks and they add pollutants and see how many of them die. So someone's built a model of that. So in effect, we would build a model of how much pollutants are getting in here and how many fish we expect to die. And then we wouldn't know. There would be a bunch of things that we didn't know. Was the assessment of a relationship between concentration of pollutants and fish death, is that well specified? or is it not very good for Lake Victoria? Or how well are things mixing in the lake? So those unknowns would end up as additional parameters in our covariance function that we would have to estimate either by maximum likelihood or by Bayesian inference. But embedded in this model would be, if there were no currents in Lake Victoria, then you would perhaps have a model of diffusion. And you might know where the pollution's coming from. So maybe the pollution's coming from here. Or maybe you don't know where the pollution's coming from, and you have a diffusion model and you have your monitoring stations, and the result is the pollution must be coming from here, because otherwise my model wouldn't work. And that's something that I really enjoy doing, is because this, now we've talked about a model that includes data, and it includes knowledge of physics and knowledge of geography. And I think that that's a lovely thing to do. That's the sort of thing one should be trying to do. It's a spatial statistics model. And in spatial statistics, they use very closely related models to this. They'll use Markov random fields, often Gaussian Markov random fields, but they're often applied in a very different way to the way people use Gaussian processes. Did that answer the question?
Maybe this is going to sound awkward, but what are the implications for correlating? Is it increase of accuracy because you've scaled down the items that you're relating? Is it?
Yeah, it's increasing accuracy. So the thing I didn't sort of probably emphasize with Ibrahim is, of course, we would have to have time as an input in order to predict in the future when the fish are going to die. And this is what we'd like to do with malaria. So with malaria, we've got rainfall, we've got vegetation. The rainfall may have an effect in the future because it takes time for the rain to settle, mosquitoes to breed, mosquitoes to propagate, and maybe time for them to take infected blood and pass it around the population. Who knows, there's some missing variables there. But if we put all that information in, then we gain, or we allow the model to know about that information could exist, then that gives us a better assessment of the way the correlations work. In general, of course, we could be completely general about a covariance and just look empirically at what the correlations are. Yeah, that would be the standard thing. And that's going to be useless because we don't have enough data to look at the empirical correlations. So things like principal component analyses are techniques for looking at existing correlations in data, where the correlation is entirely driven by the data. What we need to have here, and what I think your question is referring to, is what the use of this doing is we're saying, before we look at the data, these are the type of correlations we expect. And there will be some parameters in that, so it's going to be flexible, but not as flexible as allowing any correlation to exist. Because if we allowed any correlation to exist, we wouldn't be able to predict into the future. We have to have some way of saying something's going on in the world. We have to have model plus data. If we don't put any correlations in a priori, we've just got data, and we can't really predict necessarily. Yeah?
So regarding the correlations you're making, would I be right to say that that implicitly takes care of the error?
No, it can't. No. One thing, it's an interesting question, because you start to get very confused about what's error and what's model once you start modeling like this, because it's kind of clear in that example where we've got f of x plus sigma that this is error and this is a model. Now we are combining, in this case, because our error is Gaussian, we can put them in the same model. But here's another thing we can start to do when we think in this way. We could start having g of, let's say not x, z plus sigma, where g of z is some other thing that's going on that is not independent across our data, but is not related to what we're interested in. So maybe our measurements of water pollution are pH measurements, and really the pollutants that are going on are heavy metals that are killing the fish. So we're not measuring a direct model of heavy metals, we're modeling heavy metals plus some corruption due to the fact that we're modeling pH. But we want to now relate this part, the heavy metal, to the fish killing. So that's kind of like noise, but it's structured noise perhaps, because we may understand something about how the pH relates to the heavy metals. And we might want to include that in the model, but it's structured noise across the model. So I think that's where it comes back to the idea that the noise is in some sense part of your model. It's, you know, you shouldn't, I don't believe you, some people would say, oh, you're putting a prior here and that's likelihood and blah, blah, blah. No, I think everything that you're saying is part of what you're saying about the world, and it all needs to be thought about. And sometimes it's hard to distinguish between what is noise and what is signal, because when you start building a complex model, you may be interested in only a part of the model and not in another part. Yeah? Other questions before tea and lovely sweet bananas? John?
Just one. I wonder if you could, might be nice to elaborate on what is difficult to do with this. Like, for example, if the function really is a quadratic, then it's going to be better to use a quadratic parametric form. So, like, you know, this is more general, but then there's expenses.
Now, so if the function is definitely quadratic, it still falls within this framework. It's not difficult to do with it. In fact, it's very easy. Because remember from before that the marginal likelihood, so let's just do P of F, of the old models we were looking at is Gaussian with zero mean, and the covariance is going to be phi transpose. We looked at x transpose before, but phi and x are sort of interchangeable. So if it's quadratic, the covariance function is simply phi transpose, where phi is 1x squared. Now then, if you've got if you're interested in the quadratic part, and then you've got noise, and that's all that's going on, fine, you can just use the old parametric thing. But if there's non-parametric corruption going on, or you've got these additional things, you can add on, so you can have the covariance as being phi transpose, plus the corrupting process kg, and add that in. And then kg is like a big complex noise function. So that example sits very firmly within the Gaussian process framework. Now, having said that, there are several examples that do not, and that's anything with jumps, sort of big stochastic jumps. So if these Gaussian processes, they can predict smooth things, and often we try and make things stationary, although they're not constrained to stationarity. But if you really got, so here's a nice example of some work that John Quinn's supervisor did with Gaussian processes. It was wind fields. So he had these lovely prior distributions. This was with a guy called Dan Cornford in Aston when I was a PhD student. At the time, I didn't really understand the work. Do we have another pen? Okay, I'll keep it. So what they were trying to do is they had measurements from satellites of, I think, wave direction. So they could see the position of the waves were blown, and they were trying to infer what the wind was. And they had Gaussian process priors in order to sort of say this is how winds look. So these priors would allow cyclones, so they would allow for wind going around in circles like this, or they would allow for wind just blowing across like this. The priors were very nice, but what the Gaussian process priors couldn't do, and they did a bunch of work to use, they used Gaussian processes, but they couldn't do it directly, is if you've got a front, in a front you get wind going in that direction here and that direction there. There's a discontinuity in the wind. As you move from here, it's sort of the wind's sort of going in this direction, and then you go through the front, and then that's what a front is. It's a discontinuity. So you had to do some work to specify the location of the front. And in the example, the lake example, if there's a body of warm water and cold water, then similar things might happen. So they don't work that well in that domain. You have to make adaptations to the framework in order to use them in those sort of domains. So yeah, that's something you have to be aware of. And of course, non-Gaussian noise is a problem, the one that we're working on with Martin and Ricardo's work. Yeah? Other questions?
You said that when you use PCL to look at correlation in existing data, and does it mean that you cannot use it to predict trends in the data?
You can. You can in certain ways with PCA. I mean, PCA, when people use PCA, they're setting it up in certain in a certain way, right? They're saying, let's say we look at data where someone's measuring water temperature and, I don't know, death rate of some fish, and they keep taking measurements at those 2 points. And they take those measurements at those points every day over like 3 months. They now have built up a correlation between those 2 measurements. And they can now make predictions, assuming the relationship doesn't change in the future, because they don't really have time in this model, and PCA will be assuming independence between these observations. If you believe that that you're taking these measurements sort of in an independent way, which you aren't really, but if you kind of accept that, then you could then use that measurement to make a future prediction that if I see the water temperature is high, then the death rate will be high because I've seen they're correlated in general. But you're making all sorts of assumptions about nothing else happening in the system. And let's say you were doing that across August, and you got all these great measurements for August. You might find that in September that doesn't work because your IID assumption, which is what you have, independence and identical distribution, the identical distribution changes because in September things are different. So PCA is fine, but it can suffer from that. If you do your PCA right, you can make those sort of predictions.
Because what will be important then will be to have models that you can model using a Gaussian and be able to predict, because the models are changing. I was looking at something like I have data on cranking, and you're measuring the forces on cranking so that you're teaching the system, and you're measuring this data, and a variation in how you perform this cranking should give an idea to how you control the process.
Yeah.
The actual
yeah.
So the variation in the task performance, because it really varies so much, should give you some idea to what someone is trying to do.
Yes. Yes. So in that case, you can definitely try and use PCA models to do that type of thing. They might not be rich enough. If you get the features of the cranking right, then PCA might be a rich enough approach to sort of model how someone's doing the cranking, and then so if you know their aim, you could use PCA, probabilistic PCA in particular, to model how they're doing the cranking, and you know their aim, and then if you've got someone else with a different aim, you model how they're doing the cranking, and then you can use probabilistic PCA to assess for a future person what the likelihood of them doing, and that's fine, that's a nice thing to do. The way to do it potentially with Gaussian processes would be to maybe predict a classification, use them so that F is going into a probability, F becomes maps to a probability, you need to do some work to do that, of whether they're doing that particular action. So you could do it with Gaussian processes as well, but PCA sounds like a fine starting approach for that type of problem, yeah. Other questions? Okay, so let's break for tea, and we'll try and start. We're going to run out of time a little bit, so we'll try and start fairly soon. So should we try just a 10-minute quick break? Yeah.